All right, Ninja Nerds, what we're going to do is we're going to go over weak acid and base calculations. Okay, so let's go ahead and dive right into these because the best way to get good at these is just, like I said, practice. Okay, well, what I'm going to do is I'm going to show you the normal way of being able to do these with ice tables, but then I'm only going to show you with the first example because I'm going to teach you a little trick to make this a little bit easier for you guys. So the first one we're going to do an ice table, but all the rest of them we're not going to because I'm going to show you this trick, okay? But I still want to show you guys how to do an ice table. All right, so first off, what is the question? It says, what is the pH of a 0.10 molar solution of this sodium hypochlorite, right? And they gave us the Ka for the hypochlorous acid being 3.0 times 10 to the negative 8. All right, so first off, before we just do anything, let's write out the equation. Let's write out this reaction. So let's write out the reaction of taking this O. So remember, sodium is acting kind of like a spectator ion. And he's such a weak acid right here that he has no effect on the solution. So we're just going to get rid of him. And all I'm going to do here is I'm going to rewrite this as O. I'm actually going to write it backwards. I'm going to do Cl, O negative. All right? And I'm going to react this with water because it's an aqueous solution. And then when I do this, it's a double arrow, meaning it can be in equilibrium. And then this guy's going to be acting as the acid. The water is going to act as the acid because he's amphoteric. He can act as an acid and a base. So he'll donate a proton, and he'll accept that proton. So he'll become HClO, and this guy will become OH negative. Okay, cool. So we have our equation here. Then what we're going to do is we're going to throw in a little ice table. So let's throw in here a quick little ice table. All right, so let's write this guy here, this guy all the way over here. Let's throw this right here, okay? And again, I should actually put their states. This is an aqueous state. This is a liquid state. This is an aqueous state. And this is an aqueous state. Okay, why do I do that? Because you never include into your Ka expression, which we'll talk about that, you never include in liquids or solids, okay? So let's go ahead and write each one of these down. So what I'm going to do is I'm going to put like a little mark here, a little mark there, and a little mark there. And then there's going to be 3 individual rows here. Okay, so the first row is going to have I, which means the initial concentration. C is going to be the change in the concentration. And E is going to be the equilibrium concentration. Okay, so what did they give me? What did they give me? What did they give me? All right, they gave me the 0.10 molar solution, which is my initial concentration of the sodium hypochlorite. Well, which one is that one? This guy right there. I just didn't draw the sodium because he's a spectator ion in this case. So what do I have here? I'm going to put in here 0.10 molar. 0.10 molar solution. Okay, H2O, what did we say? We don't even include him at all because he's not even included into the Ka expression because he's in the liquid state. HClO, well, they didn't give me anything for them. So if he didn't give me anything, it's got to be 0 then because I don't know what he is. So he's got to be 0. Same thing for the hydroxide. They didn't give me anything with the hydroxide. So he also must be 0. Okay, now, if you think about a reaction kind of like this, like as this reaction is occurring, what's happening to the concentration of the hypochlorite as this reaction is proceeding towards the products? He should be decreasing. So if his concentration is decreasing over time, his change in concentration at equilibrium should be decreasing. So if that's the case, then we're just going to say we don't know how much changing, but we denote that as minus X. So that's the amount that this is changing throughout the progress of this reaction. Okay, but we don't know what X is. So we just denote that this is decreasing by X. So what's our equilibrium value then? Well, we have to put this in. So I plus the C then here. So it's going to be 0.10 minus X. Well, these guys, they got to be changing, but they have to be changing and their concentration is going to be increasing during the process of this reaction because as he is decreasing, this concentration of these products are increasing. So this is increasing by some factor of X, and this is increasing by some factor of X. So again, we do I plus C, so it's just 0 plus X, which is X. 0 plus X, which is just X. Now what we're going to do is we're going to take and plug all of these equilibrium values into our Ke expression or Ka expression specifically. But let's make sure that everything is balanced here. So I got 2 hydrogens, we're good there. I got 1 chlorine, I got 1 chlorine, I got 1 oxygen, 1 oxygen, 1 oxygen, 1 oxygen. So it's balanced, that's good. We need to make sure it's balanced. Always check and make sure your equation is balanced. In this case, it is. Now we're going to do over here, I'm going to do it over here. I'm going to put it over here a little bit. We're going to write out the Ka expression. So the Ka expression says this, that the Ka is equal to the concentration of your products raised to their stoichiometric coefficient. So for example, if there was a 2 in front of this, I would have this guy's concentration raised to the second power. If this guy, if he was raised, let's say he had a coefficient of 3, then he would be raised to the third power, and their factor change of x would also increase by that coefficient. So if, for example, this was 2, it'd be plus 2x change. If this guy was 3, he'd be a plus 3x change, but you would also raise them to the second power and third power. But since it's 1, it doesn't matter. So it's Ka is equal to the concentration of the products, which we're going to put HClO, right? But what is the concentration of him at equilibrium? It's x. We don't know what it is, so I'm going to put x there. Then I'm going to take the hydroxide ion concentration at equilibrium, because he's another product. He is x. And then what I'm going to do is I'm going to put underneath that the concentration of my reactant. So I go down to E, equilibrium. I'm going to put that in. So that is 0.10 minus x. And they gave me the Ka value. But here's the problem. This is not an acid. This is a base. We don't want the Ka value for this reaction. We want the Kb, because that'll determine the rate at which this hypochlorite is reacting to produce hydroxide ions. So we don't want the Ka. Well, how do I get the Kb? So if you remember, we said Kw, which was the autoionization of water constant, which was 1.0 times 10 to the negative 14, is equal to the rate of acid ionization times the rate of base ionization, right? These constants, if you will. So more specifically, these constants, right? So now, what do I do here to get Kb? Well, I got Ka. I already know what Kw is. What is it? It's going to be 1.0, so let's actually write that down here then. What would it be? It would be 1.0 times 10 to the negative 14, and I'm going to have to divide over Ka so that I can get Kb. So Ka is what? 3.0 times 10 to the negative 8. Okay, so what's that going to give me if I plug this into the calculator? Let's do this. So we take and we do 1.0 second e to the negative 14 divided by 3.0 second e to the negative 8. What does that give me? That gives me 3.3 times 10 to the negative 7. Let's write that down. 3.3, I'll put one more sig fig in there, 3 times 10 to the negative 7. Okay, cool. That's my Kb. So I don't really want Ka. What do I actually want there? I want Kb. So I'm actually going to replace that with Kb. So now let's go ahead and put it under here, and let's actually solve this thing out. So what do I do here? I'm going to say that Kb is 3.33 times 10 to the negative 7, which is equal to x. Now, what would this, if I simplify this, what's x times x? X squared. So this is x squared. And then under that, I'm going to have 0.10 minus x. Okay, here's where it's going to get, a little different. What you can do is, because if I do this, if I kind of multiply this out and I cross multiply, I'm going to end up having to do the quadratic formula. I don't want to do the quadratic formula. I don't like doing that. So sometimes you might have to, but in this case, let's see if we don't have to. In other words, I'm going to assume that change in x, so the change in the concentration of the hypochlorite over time, was so small that it didn't even matter. So what do I mean? I'm going to blast this x out of here. I'm going to consider that x to be 0. I'm actually just going to get rid of that and all. So now what do I actually have out of this? If I were to erase this, then what would it be? It would be 0.10. So again, assume that x, there's a way to check and make sure it always works, but always try to see if you don't have to do it first. So you assume that x is 0, and now what am I going to do? I'm going to cross multiply and take the square root. So what is that? I'm going to go ahead and do 0.10 times 3.33 times 10 to the negative 7, which equals x squared. Well, what do? Algebraically, you take the square root of this, and you also take the square root of this. So let's go ahead and plug that in, and let's get what x is. So x is going to be 0.10 times 3.33 times 10 to the negative 7, and then we're going to square root that. And we get 1.83 times 10 to the negative 4. Let's write that down. 1.83 times 10 to the negative 4. Okay, so now what do? All right, well, I want to make sure that I told you, I want to make sure that this is right, that I can actually assume that this number is so small that it's completely insignificant. So there's a way that you can check this. This guy right here is supposed to be your hydroxide ion concentration. That's what he's supposed to be because that's X. So what do? I'm going to take this equilibrium concentration of my hydroxide ion, which is that 1.83 times 10 to the negative 4, and I'm going to put that over the initial concentration of this weak base right there, which is 0.10. So what would it look like over here? I would have hydroxide ion concentration over ClO negative concentration, right? That's basically what I'm doing here. I'm going to take and divide these guys, and then I'm going to multiply it by 100. And I'm going to get a percentage, and I better hope that that percentage is less than 5%. So let's check that out. I'm going to take that number, and I'm going to divide it by 0.10, and I'm going to multiply that by 100. And I get 0.18%. Sweet. I'm digging it, 0.18%. So what does that mean? It's less than 5%. If this is less than 5%, that means that that number that we had, that minus X, is insignificant, and it didn't matter. So no matter what, if you were to subtract that number, 1.8 times 10, 3 times 10 to the negative 4 from this number, it would still be pretty darn close to 0.1. So it was insignificant. It didn't matter. So okay, if that's the case, then that's my concentration of the hydroxide. So now what I do? This is my hydroxide ion concentration. Well, I want pH. Well, too bad. I'm going to get POH, and then I'm going to do 14 minus that to get the pH. So what do I mean here? That's my hydroxide ion concentration. So what do? All right, so now I said that this number right there, that 1.83 times 10 to the negative 4, molarity, I should put molarity. Let me be very, very specific here. Keep my units there. Molarity, that's the hydroxide ion concentration. So what do I need to do here? I need to take the POH, right, which we said was the POH is equal to the negative log of the hydroxide ion concentration. Well, what is it? It is 1.83 times 10 to the negative 4 molarity, right? So if I go ahead and take the negative log of this, let's say I take the negative log of 1.83 second e to the negative 4, what do I get? I get 3.74. So what's my POH? My POH is equal to 3.74. So now what I have to do is, I want the pH. So pH is equal to the 14 minus the POH. So what's 14 minus 3.74? I don't know, let me check. It is 10.3. So this is 10.3. Now, this is a long problem to just get to that answer. I'm going to show you guys in number 2, way easier way to bypass all of this gibberish, all right, to get your answer a lot quicker. But again, what do we do in this problem? Just so that we know how to do it if we need to. Using an ice table, you write out your initial, your change, your equilibrium. And remember, if it's anything is in the liquid or the solid state, he's not even a part of the Ka expression or Kb expression or Ke expression. So you just cancel him out. All right, so then write all those concentrations in respectively. If it had an initial, if it didn't have an initial, the changes, which is always minus for the reactants and plus for the products. And then just basically take your I and your C and add them together, and then you'll get your equilibrium, which in this case is 0.1 minus X, and this is 0 plus X, which is both X. Then you plug them into your K. In this case, it was the Kb expression. And we just put products raised to their stoichiometric coefficients over the reactants raised to their stoichiometric coefficients. But it just happened to be 1 for each one of those. So you plug them in here, and then for this one we had to get Kb because they gave us Ka. So we just take Kw and divide it by Ka to get Kb, which was 3.33 times 10 to the negative 7. Then we had to plug it back into this Kb expression, but what did we do? We assumed that that X, that minus X, was so small that it didn't even matter. And we just assumed that it was just 0.1. And then we did that, we just cross-multiplied and took the square root of the multiplication of these two, and we got this concentration. But we wanted to check. How do you check? You take the equilibrium concentration of your hydroxide, and you put it over the initial concentration of this weak base. All right, the initial concentration, and you multiply it by 100. If that number is less than 5%, you can assume that that minus X is 0. Now, we're going to blast through all of these a lot faster because there's an easier way to just bypass all that. So let's go on to number 2. What is the pH of a 0.20 molar solution of N2H5Cl? Hydrazine is a weak base with Kb 1.7 times 10 to the negative 6. All right, so let's write out this equation. So what were we given? What was our initial thing? We were given N2H5Cl. So let's write this guy down. We were given N2H5Cl, N2H5Cl, okay, and this is our hydrazine. I'm sorry, they said hydrazine is a weak base with this Kb. So then what happened? Then this guy must be, in some way, shape, or form, he must be acting as like an acid. Now what I'm going to do is, this chloride ion is a spectator ion. In other words, remember we talked about this in the acidity and basicity of salts. Hydrochloric acid is a strong acid. Its conjugate base is chloride, which is so weak it has no effect on the pH. So he is a spectator. If that chloride ion has a negative charge, what does this guy have to have? He has to have a plus charge. Okay, so N2H5, he's acting as an acid. So what does acids do? Acids do what? Okay, let's say we react this with water, and we get the equilibrium reaction here. He's going to give up a proton onto the H2O, so you'll get H3O plus, and you'll get, what happens? He loses a hydrogen, N2H4. Okay, now remember, we had an ice table before. I'm not going to use an ice table in this reaction right here. I'm going to just bypass that. Now I'm going to show you, I'm going to write out the equation that I want you guys to remember. Write this down and forget all of this stuff over here. I mean, keep it in your mind, but use this equation primarily. Here we go. This equation we're going to use is, you take the concentration of the hydronium ion and you make it equal to the square root of the Ka times the concentration of your weak acid, which we denote as HA. Okay, so in this case, what's our weak acid here? N2H5 plus. Let's actually put him in there then. N2H5 plus. Okay, how did I get this? Let's come back. No, let's actually show it here. I'll show it here real quick because this is going to be a quick calculation. What do we do then? Remember before we said that if we were to write out the whole Ka expression, the Ka is equal to the concentration of your products, which is going to be X and X, right? Because, again, you weren't given any initial concentration of these. So you're going to get used to these problems and see that the equilibrium is just X. So these two is X times X. So you get X squared, like we did in this number 1. And then we're going to put that over his initial concentration, but we're going to do that minus the change, which is 0.20 minus X. Remember what we did before? We assumed that X was just like 0. We assumed it was so small that it was insignificant, but we have to check it always. What do? We said that we just took the 0.20 molar concentration, multiplied it by the Ka, and then what do? We square rooted it to equal X. What did X equal before? It equals the H3O plus concentration. Just like in the other one, it equaled the hydroxide ion concentration. So you see what I did here? X is H3O plus. Ka, the 0.20 molar is the initial concentration of our weak acid. It's so easy, right? So now what do? Let's just plug everything in then. So H3O plus, which is our X, is equal to the square root of our Ka. Oh, look, they fricked with us again. They gave us a Kb. Well, what do? We take Kw, divide it by Kb to get Ka. So how do we do that? Kw is 1.0 times 10 to the negative 14, and we're going to divide that by Kb, which is 1.7 second e to the negative 6. And what do we get? We get 9.35, I'm just going to put 9.3, times 10 to the negative 9. So I'm going to plug that in here. 9.3 times 10 to the negative 9 times the initial concentration of our weak acid, which was 0.20 molar. Okay, so let's plug this into the equation and just go ahead and multiply that. So multiply that by 0.20, and then we're going to take the square root of that number, guys. And we get 4.3. What do we get? We get 4.3 times 10 to the negative 5. Okay, remember what I said. Do not just assume that that's the answer, because you don't always know if this is always going to work, but there's a way that you could bypass it again. So what do you do here? You take this guy right here, the equilibrium concentration of your H3O+, and you divide it by the initial concentration of the weak acid. So what would that be? It would be 4.3 times 10 to the negative 5 divided by 0.20, and then you multiply it by 100. Remember that? And it has to be less than 5%. What did I get when I did that? I got 0.021%. That's less than 5%. So what does that mean? That means that that x that we got rid of there, this one it had that minus x and we got rid of it, we blasted that out. That means it was so small it was insignificant. It is 0. So what does that mean? I have my H3O plus concentration. Well, how do I get pH? pH is the negative log of this. So pH is the negative log of the hydronium ion concentration, which is 4.3 times 10 to the negative 5. And we're going to get somewhere in between 5 and 4, so it's probably going to be like 4 point something. Let's check this out. So negative log of 4.3 times 10 to the negative 5, guys, and we get 4.4. Okay, we're going to say 4.4 here. So pH is equal to 4.4. Okay, and that's basically going to be an acidic substance. So that's good because we started off with an acid. All right, so that's 2. Let's go on to 3. But now that we know that trick, let's just go straight to the trick. Let's go ahead and bypass all that other stuff. All right, so let's go ahead and do this next one. But again, we already know how this works. Okay, so what is the question? Calculate the pH of a 0.20 molar hydrocyanic acid, right? So HCN. So we're going to have our HCN right here, solution. And we're going to have the Ka for that HCN, which is going to be 4.9 times 10 to the negative 10. It says identify conjugate acid base pairs and calculate the pH. So let's go ahead and do our conjugate acid base pair. So we have HCN, our hydrocyanic acid, right? And what are we going to do here? It's going to react with water. And since it's not a strong acid, it has a equilibrium, so it's a reversible reaction. HCN is the acid. He gives up the H to the water, who turns into H3O plus, and then HCN loses its H and it turns into cyanide, right? And they said that the Ka for this reaction is 4.9 times 10 to the negative 10. Okay, cool. So identify the conjugate acid base pairs. Well, he is the acid. He is the base. And then what happened? We said that this guy, HCN, got converted into Cn negative. And Cn negative is the conjugate base. So he is the conjugate base. So this guy goes here. And then H2O turns into a conjugate acid. So this is the conjugate, so this is the base conjugate acid pair. So we have our acid conjugate base pair and base conjugate acid pair. Super easy, right? Not too bad. What did we say before? Let's bypass all this stuff that we did before, the ice tables and explaining what happens, and we just put in H3O plus is equal to the square root of the Ka, in this case 4.9, times 10 to the negative 10, times the initial concentration of the weak acid, which is 0.20, and then we're just going to square that. And we're going to check it. And we're going to make sure that that works. If it doesn't, I'll show you how you get around that. So 0.20 times 4.9 second e to the negative 10. And then what I'm going to do is I'm going to square root that. And then I get 9 so for this guy, H3O plus, I get 9.9 times 10 to the negative 6 molarity. All right, so I'm going to take this number and divide it by 0.20. There's no way that this is going to be greater than 5%, but I'm going to do it anyway just for the sake of it to show you guys. And I'm going to multiply this by 100. And when I do it, I get 0.005%. That's so much smaller than 5%. We know that that minus x over there, it's definitely going to be 0. Blast that x out of there and just use this equation. Okay, well, we got to get pH. What do? Take the negative log of the hydronium ion concentration. So pH is equal to the negative log of hydronium ion concentration, which is 9.9 times 10 to the minus 6 molarity. And if I do that, what do I get? I'm going to take the negative log, and it's probably going to be somewhere, in between 6 and 5, so some 5 point something here. 9.9 second e to the negative 6, and we get out of this 5. So I get a pH of about 5, which is good. Because again, we said that this is a weak acid, so it shouldn't be down on the pH scale, it should be a little bit up. That makes sense, that should make sense. Okay, cool, now let's go ahead and move on to the next one over here. right, so let's do this last one, guys. So it says calculate the pH of calculate the pH and hydroxide ion concentration in a 0.15 molar ammonia solution and identify conjugate acid base pairs. Okay, so we got ammonia. We know that ammonia, just try to remember, guys, that ammonia is a weak base. So this is one to actually kind of commit to memory, that ammonia is a nice weak base. Okay, and then what happens? We're going to react this with water. If we react it with water, what happens? Then what's going to happen is this is going to be equilibrium again because it's a weak base, so it's not strong. NH3 is a base, so he accepts protons. So H2O is going to act as the acid. So we're going to get NH4 plus hydroxide. Okay? And again, if that's the case, then this is our base, the NH3. The water is acting as the acid. The ammonium is acting as the conjugate acid. I'm going to put conjugate acid. And then the hydroxide is acting as the conjugate base. Okay, so what's our pairs here? If we do our pair thing again, we have NH3 going to NH4, so that's a base conjugate acid pair. And then we have water going to hydroxide, so that's our acid conjugate base pair. All right, cool. Same thing from before, guys. This is a weak base. So I'm going to bypass all that other stuff, and in order for me to remember this, I remember this equation. So it's not just the H3O plus concentration. That H3O plus concentration is the same thing for hydroxide. So what does that mean? For the H3O plus, what was it? Let's write that one out so we can compare. H3O plus concentration is equal to the square root of Ka times the initial concentration of your weak acid. We'll just put HA in this case. The hydroxide ion concentration is equal to the square root. It's not Ka anymore, it's Kb, and it's not a weak acid, it's the weak base concentration. Okay, cool. So let's go ahead and plug this in. Hydroxide ion concentration is equal to the square root of the Kb. What's our Kb here? Well, the Kb of ammonia, it was, we did it over there in the acidity and basicity of salts. It's 1.8 times 10 to the negative 5. Okay, so then that's going to be going right there. So 1.8 times 10 to the negative 5, that's our Kb, and then we multiply by the concentration of our weak base. What was our weak base? Ammonia. What's the concentration? 0.15. Plug that in. Now remember, it would have been, if you did the whole ice table, it'd be 0.15 minus x, and then you'd had to do all that other stuff. We're going to bypass all that and try to assume that the x is 0. And I'm going to show you after this what you would do if it wasn't actually less than 5%. I'll show you. All right, so let's do here square root. All right, so let's do this. 0.15, and we're going to multiply this by 1.8 second e to the negative 5. And I'm going to square root that, guys, and I get 0.0016. So hydroxide ion concentration is equal to 0.0016 molarity. So that's that first question that we answered, the hydroxide ion concentration, right? And then we did our conjugate acid base pairs. Now, what do we do? To make sure that this is so small that it's insignificant, I take the 0.0016 and I divide it by the initial concentration, which was 0.15. And then I multiply it by 100. And I get 1.09%. All right, so what we do here for this one again, so we'll take that, in order for us to get the pH, well again, what is this? One thing we can do from hydroxide is we can do POH is equal to negative log of the hydroxide ion concentration, which is 0.0016. And then what do? We take the negative log, so let's take the negative log of that negative log of 0.0016, guys, and we get 2.8. And then what do? We want the pH, right? Not the POH, so I just do 14 minus 2.8. So 14 minus 2.8, and what do I get? I get 11.2. So my pH, which is the thing I'm looking for, is 11.2. And again, that should make sense. Why? Because this is a weak base. So he shouldn't be close to 14. He should be getting a little bit closer to around the 7-point line, right? All right, engineers, so we talked a lot about weak acid and weak base calculations, and we went into a lot of detail. One thing I want to do in the next video is I want to go ahead and talk about percent ionization, and I want to talk about what happens if this little trick I taught you doesn't work, and it's actually greater than 5%. And we'll have to go through the quadratic formula, and I'll show you guys that. Click up on the right icon on that video, and I'll see you guys soon.